Section 6.3, Volume of Revolution, Cylindrical Shells. In the last section, we looked at how to find the volume of a solid of revolution that was formed by rotating a region around the x-axis. And the methods we used were either disk method or washer method, because the cross-sections were either disks or washers. In this section, we're going to look at a method for finding the volume of a solid of revolution when that solid is formed by rotating a region around the y-axis. We're going to let f of x be a continuous, non-negative function, and we're going to define r as the region bounded above by the function f of x, below by the x-axis, and to the left by the lines x equals a, and on the right by the line x equals b. Then the solid of revolution formed by revolving r around the y-axis is given by v equals the integral from a to b of 2 pi x f of x dx. The reason for this formula is because if we look at the first figure below, we can see a region formed by f of x, and take note of the rectangle that is drawn in blue. When that rectangle is revolved around the y-axis, it is going to create a cylindrical shell that we see in the second figure. The formula for finding the area of a cylindrical shell is 2 pi r h. If we take a look at what the radius of the shell is, that would be how far the shell is from the y-axis, which would correspond to how far the rectangle is from the y-axis in the first picture. So the radius would be equal to x. As for the height of the shell would correspond to the height of the rectangle, which would have a height of f of x. So the area of our cross section, a of x, would be 2 pi, replace the r with x, and the h with f of x. And as we've seen in the previous section, to find the volume of a solid when we know the area of its cross sections, and as we can see in the last figure, we can see that each cross section would be a cylindrical shell. So we would integrate our volume over our area function over the interval ab, and that's how we get our formula for the shell method. Now we're going to find the volume of the solid generated by revolving the region enclosed by y equals 2e to the 5x squared, the x-axis, x equals 0, and x equals 1 about the y-axis. Just like in past problems, we're going to start by sketching our region. X equals 0 and x equals 1 are vertical lines, and we know the x-axis is part of our bounds for the region, so we'll highlight the x-axis in blue as well. As for the 2e to the 5x squared, we know the general shape of e to the x. Because 5x squared is positive when x is between 0 and 1, then this portion of the graph would look similar to what we would see for an e to the x graph, which would look something like this. Note that I'm not worrying about finding the intercepts with x equals 0 and x equals 1. I know 2e to the 5x squared is always a positive value. So I know its graph will lie above the x-axis. And the intersection points wouldn't necessarily be needed here, because we can clearly see that this would be a rough sketch of our region, which I have shaded in pink. Since we're revolving around the y-axis, that tells us we're using the shell method to try to find the volume of the solid. So we're going to set up our integral, which here will be from 0 to 1, because the smallest x value is 0, while the largest x value is 1 within our region. As for our integrand, according to the formula, it is 2 pi times x, and then our function, which is 2e to the 5x squared. And when we simplify, we have to find the integral from 0 to 1 of 4 pi x e to the 5x squared. To evaluate this integral, we do need to make a substitution. We'll make u 5x squared, which makes du 10 dx. We do see an x in the integrand, so let's divide over the 10, and we get that du over 10 equals x dx. Now we can go ahead and substitute to see if our integrand can be written completely in terms of u. 4 pi will stick around. The e to the 5x squared becomes e to the u, while x times dx becomes du over 10, which we can clean up to 2 over 5 pi e to the u du. Since our integrand is completely in terms of u, we can go ahead and change our bounds. If x is 0, u would be 0. If x is 1, u will be 5. So our bounds for our integral will become 0 to 5. Now find our antiderivative. The antiderivative of 2 over 5 pi e to the u would be 2 over 5 pi e to the u, which would be evaluated from 0 to 5. And if we plug in our bounds and simplify, we get that the volume of our solid is 2/5 pi e to the 5 minus 2/5 pi. Next, we're going to find the volume of a solid generated by revolving the region enclosed by y equals negative x squared plus 3x minus 2, and the x-axis about the y-axis. Just like all of our previous problems, we want to start off by sketching the region. This time, the only equation we have to graph is the y equals negative x squared plus 3x minus 2, which we know would be a parabola that opens down. But to help us with our bounds, let's see where it intersects the x-axis, which means we're trying to find its y-intercepts. So we'll set our quadratic equation equal to 0, and we can solve our quadratic equation by factoring, and we get that x is 2 or 1. So y equals negative x squared plus 3x minus 2 would look a little something like what we have in blue, and the region that is enclosed by this parabola in our x-axis would be located here in green. Since we're revolving around the y-axis, then we are going to use the shell method to figure out our volume. So the volume would be the integral. As for the bounds, they would be our intercepts, which is 1 to 2. Our integrand would be 2 pi x times the equation of the function, which is negative x squared plus 3x minus 2. Now, the problem with this integral is that there is no product rule to find the antiderivative, and a substitution won't work, since if I make the u negative x squared plus 3x minus 2, the du would be negative 2x plus 3, which wouldn't help us substitute away the x. So what we're going to do is we're going to distribute in the x. That way, there's no more multiplication with polynomials. And then I can find the antiderivative of the negative x cubed plus 3x squared minus 2x using power rule. You could also distribute in the 2 pi, But since 2 pi is a constant multiplier, then that would just be multiplied to whatever the negative x cubed plus 3x squared minus 2x's antiderivative would be anyway. So it's up to you whether or not you want to distribute into 2 pi. For simplicity, I would keep it factored out though, since it's just a constant. As for the antiderivative, it'd be 2 pi because it's a constant multiplier, times, now applying power rule to the polynomial, and we get negative x to the 4th over 4 plus x cubed minus x squared. Now we can plug in our bounds and simplify, and we get that the volume is pi over 2.